Welcome to the Mizzou Cloud and DevOps curriculum series for online learning. My name is Songji Wang. I am a cyber infrastructure engineer at the University of Missouri, Center for Cyber Education, Research, and Infrastructure. In this video, I'm going to briefly go over the second lab in our learning series, Lab 2, Software-Defined Networking on AWS with Cyber Defense Application. The purpose of this lab is to help users to learn how to set up software-defined networking, as known as SDN capability, using Virtual Extensible LAN protocol on a public cloud, Amazon AWS. The topics for this lab include technology. We use software-defined networking using Virtual Extensible LAN, and the platform, in this case, Amazon AWS Cloud Platform. The use case application, Doulos Cyber Defense by Pretense application. SDN is an approach that allows us to manage our network and then enables a dynamic and a programmatically efficient networking configuration. SDN allows us to program our network independent of the switches in the network topology, and thus allowing us to separate the control plane and the data plane in a traditional network. By decoupling this control plane and the data plane, the users can easily program the controller plane and thus allow the users to control where the data are transmitted on the network. Traditionally, SDN is largely not feasible on a public cloud because cloud providers do not allow users to manage and manipulate their switch devices. In this lab, we explored using Virtual Extensible LAN to create a virtual network on top of the Layer 2 and the Layer 3 network on the public cloud, and thus allow us to manage our network configuration and the network routing between the nodes. In this lab, we use a use case application called Doulos. Doulos is a cyber defense by pretense application that is used to detect and mitigate target cyber attacks, including DDoS attack, advanced persistent threats, advanced persistent mining, also known as cryptojacking attacks in the network. Doulos include topology with several nodes, including a SDN controller and various servers, users, quarantine machine, and network switches. Doulos use SDN-based networking mechanism to redirect the network connection from the attacker to the server in the topology to a quarantine machine that we create in the topology. By redirecting the network connections from the attacker to the quarantine machine, we're protecting the servers in the network topology so the legitimate users can still use the server while the attackers are actually defeated. Doulos also send a fake response packet to the attacker, pretending that this packet is sent from the server, so the attackers are tricked by thinking that they're still attacking to the server, but in the actual, they have been defeated by the Doulos system. In this lab, we'll guide the students to learn how to set up the software-defined networking capability using Virtual Extensible LAN on AWS. We'll create an SDN virtual network with a frenetic controller as the control plane, and then we'll create two Open vSwitches, including a root switch and a slave switch. Each of these switches are connected to the controller via TCP/IP connection and has host in the network attached. We'll then create a number of host machines that are connected to these switches via virtual extensible LAN network overlay to mimic the servers, users, and attackers in the network topology. At the end, we'll practice to use the doodles to control network connections between these nodes and then collect sample network connection packet data. For this lab, you will have to access the lab instructions from our Mizzou Cloud DevOps.net to access the PDF instructions to be able to execute this lab. The lab steps are listed below. First, we provide an overview of this lab with some information about software-defined networking, AWS Cloud, and the Docker containers that we will use to execute this lab. Before you start working on this lab, you will need to have a lab account on AWS. So we provide AWS Educate account for each of the users, and with some free credits that you can use to pay for the cost of using AWS resources. For you to be able to have such an account, please send an email request to us and a request for such an account to be set up for you. The main tasks of this lab include: first, you will create a topology and configure virtual extensible LAN on the AWS EC2 instance. The second task, you will then install the Doodles system and initiate software-defined networking using the Frenetic controller. The third task, you will use the Doodles system to control the network routing within the topology and then collect some sample network packet data from the nodes. After finishing up all these tasks, you will clean up your lab resources by either stopping or deleting the AWS EC2 instance from your account. In this video, I'm going to show the demos of all these three tasks, so you have an idea of how each step is working and what you expect to see after you execute the lab steps. Task 1. Creating the topology and configuring the virtual extensible LAN. Let's switch to the command line console here, and we wanted to guide you through the rest of the lab execution. Before you continue with the lab steps, please make sure that you already created an AWS EC2 instance, logged in as the Ubuntu user, and installed Docker and Docker Compose on it by following the lab instruction. Once you have downloaded the Doodles SDN demo GitHub repository, you can go to the directory and run the Docker Compose op-d --build command to start the Docker containers. During the Docker Compose command, you will see that you will use the pre-built base images for both the Doodles controller and the other nodes for building your own Docker image on your EC2 instance, and install a whole bunch of libraries on each of the nodes. We will fast forward this installation process, and at the end of the installation, you will see that you already created all the Docker images and it started the 7 Docker containers in the topology. Once you see that all the Docker containers are created, and you can run a docker ps-a command to show all the running Docker containers on your instance. Once you see that all the Docker containers are up and running, now we're going to run the ovs configure shell command to install the Open vSwitch on each of the nodes and start the virtual extended LAN on each of the nodes. By installing the VXLAN in your Docker containers, you have created a topology within your AWS EC2 instance that is built in the Docker network. After you configure the OVS, you can run the OVS vsctl show command to see the configuration of the OVS in one of your nodes. For example, you can run docker exec root switch with the OVS vsctl show to see the interface within your OVS configuration. The example here shows that on the root switch we have two network interfaces, ETH1 and ETH2, each connected to one of the other nodes in the topology. Similarly, you can run the same command on other switch or other nodes within the topology to check the OVS configuration on that specific node. After you successfully configure the OVS on all of the Docker containers, you can run a ping command to check for the network connection between your nodes in the topology. You can see from the demo here that we initiated a ping connection from the attacker node to the other node in the topology, and then we have received responses from the other nodes in the topology. This indicates that our virtual extended LAN has been successfully installed in our Docker containers within our AWS EC2 instance. Task 2. Installing the Dulo system and initiating the software-defined networking using Frenetic controller. At this stage, we're ready to configure the software-defined networking in our topology. For this step, you will need to open up a total of 10 command line terminals, 2 for the controller node, 2 for the root switch, 2 for the slave switch, and 1 for each of the other nodes. From the first terminal on your controller node, you will need to run the Frenetic controller to control the software-defined networking in the topology. You can copy the command from the lab instruction, and once you see the output similar to what we were showing in this video, and your controller is up and running, and it's going to control the network connections within your topology. Now switch to the root switch. You are going to run this OVS vsctl set controller command to connect your root switch to the controller. On your controller node, you can see in the flow table that you already have this DPID of the root switch in the flow table. That means the root switch has been successfully registered to the controller. From here, you can follow the lab instruction to export the DPID of the root switch to a variable, or use the number later when you configure the database. Now change to the first terminal of the slave switch and then run the same command to set up the controller for the switch. Go back to the controller node. You can see in the flow table a second entry has been added, which is the DPID of the slave switch. You can export this DPID of the slave switch as a variable, or you can use a number to set up the database later. Once you have set up the root switch and the slave switch connected to the controller, now you can open up your web page and then connect to the Doulos project. By inputting the IP of your AWS EC2 instance to access the admin UI of the Doulos project. But please do not try to register or log into the Doulos web UI yet. At this stage, we need to update the database in the backend to reflect the changes in our software-defined networking. On the right-hand side of the command line, you can see that we're running this bash database update shell script to update the database with the DPID of the root switch and the slave switch. You can use the variable that we created earlier, or if it has issues, you can use the integers for these two DPIDs to update the database. Once you see from the green output that the admin UI has been properly configured, your Doulos system has been correctly installed on the EC2 instance, and now you can complete the rest of the lab. In the next step, we're going to log into the database to verify our information. By following our lab instructions, you can log into the database by using this Monty user and then connect to the test database. From the test database, you can check all the tables that are created in the database, and you can also check the information for each of these tables here. For example, you can select all from the devices and then to see what are the devices that are attached in the topology. Here you can see the attacker, the QVM, and the user, which are basically the users in the topology. Feel free to check other tables as well using the similar commands. After we verified the information in the database, now we're ready to create a user from the Doulos web UI and then log in to the web portal. From the web portal, you can see there are a comprehensive list of functionalities that you can click to view the information of the nodes in the topology, the history of network connections, and then history of attacks, and then user migrations, etc. The Doulos web UI gives you the capability to view the information in our topology, but it does not control the software-defined networking. To be able to control the software-defined networking, we're going to run a Python script that is located in the Doulos project directory on the EC2 instance. On the command line, you can see that we already switched to the Python directory within the Doulos project, and then we used the seed command to update the DPID of the root switch and the slave switch in the Python code. So this Python script is called Open Network Adapts. This is the main Python code that we're going to use to control the software-defined networking in the topology. Feel free to examine the Python code and see how it uses frenetic programming interface and the netcat policy to control the network in the topology. Interested users can search for a frenetic programming guide to learn about the syntax and how frenetic can use the flow table to control the network connections in the topology. Now with the frenetic program is running in the controller node, you can try to run a ping command from attacker node to the other nodes in the topology. You can see that the ping command will fail. This is because although the frenetic is running in the controller node, our software-defined networking, the Python code, is not running yet. Without the Python code running the SDN, the flow table in the controller will be empty, so there won't be any network connections between any of the nodes in the topology. Now if you start the SDN by running the Python code, and then switch back to the controller node, you can see there are multiple entries for each of the switches in the flow table. In each of the entries, we're seeing that for a specific destination IP in the topology, the network packets will be forwarded to the appropriate port in the OVS setup as shown in the output. With this SDN setup, now if you try to run the ping command again from a specific node, you will see that the ping command is now working, and then you got responses from the target IP in the topology. So at this stage, you have successfully created a topology and running the controller node with the software-defined networking to control the network connections between any of the nodes in the topology, which means your software-defined networking is up and running. Task 3. Use the Doodle system to control the network routing and collect some sample network packet data from the topology. In the third task of this lab, we're going to use two utility tools running on the root switch and the slave switch to collect some sample data in the network topology by running the SDN. These sample data will be loaded into the database in the Doodle system and later used to analyze and detect any cyber attacks in the topology. These two tools are called T-Shark and Bandwidth Monitor. So you can follow the lab instruction to run the T-Shark and Bandwidth Monitor utilities on both of the terminals for the root switch and the slave switch. So on one of the terminal, you will run T-Shark, and the other terminal running the Bandwidth Monitor. While these utility tools are running on both of your root switch and slave switch, you can start a new ping command from any node in the topology or leave your old ping command running. If you switch to the first terminal of both the root switch and slave switch, you can see that T-Shark has already collected several hundreds of network packets from the ping command that you're running on the other node. So the T-Shark collects the information of each of the network packets, while the Bandwidth Monitor collects the data in terms of the bandwidth consumption in the network. Both of the utility tools will save all the data that they collect into CSV files on your EC2 instance so you can process them later. In this lab, we'll just display the data on the standard output and show you how they look like. Now we're running the head command with an option of -n20 to display the first 20 entries in the CSV file. You can see that the T-Shark has collected a whole bunch of information about each of the network packet in our ping command. For example, the frame number, the timestamp, the source and destination IP and port, and protocol, etc. From the same switch, by running a similar head command with an option of -n20, we're going to display the first 20 entries in the stats.csv file, which is the output from the Bandwidth Monitor program. From the screen here, we can see the output from the Bandwidth Monitor program. The data shown us the timestamp of the bandwidth with the name of the interface the bandwidth is tested on, with a bunch of numbers following the network interface. The first three numbers tell us the size of the packets that has gone out, come in, and the total from that specific interface. And then the next three numbers indicate the number of packets that has gone out, coming, and the total from that interface. While the last two numbers indicate the error packets that has gone out and coming to the interface. In this case, they're both zeros for all of the packets. Similarly, if you change to the slave switch terminals and check the CSV files on that node, you will notice that similar data have been collected in the CSV files, but they're specific to the slave switch in terms of the number and the size and the frequency, etc. Okay, so at this point, we have showed you how to set up software-defined networking using Docker containers on AWS EC2 instance. And we showed you how to collect some sample data by running the SDN and use the T-Shark and the bandwidth monitor programs to collect data in terms of network packets, bandwidth usage, and etc. in the SDN network. In this lab, we're not going to show you how to process and analyze the data using machine learning to identify cyber attacks in the topology. Rather, these will be introduced in our another learning series, the Cyber Defense Labs. Interested users are encouraged to contact us to obtain the learning materials for the Cyber Defense Labs. Thank you for watching this video, and I hope to see you in the next lab.